So I don't need to introduce myself again. And can you see my screen? Okay. Yes, good. Here we are. So you get to hear from me about a lot of math. I hope everyone is very excited about this. So I will tell you about two different training objectives for GFlowNets. You heard about flow matching and how optimizing a flow matching objective at every state in a GFlowNet leads to getting a policy which can sample objects in proportion to their reward. And I will motivate and introduce two new objectives called detail balance and trajectory balance, which are the ones that we most often use in practice in applications of GFlowNets. And I'll conclude with some discussion of how to train your GFlowNet. Now, just to review and to set up background. Unfortunately, my figure is not animated, but this is the kind of figure that we just saw in Emmanuel's talk. We have a directed acyclic graph, which specifies the structure of a generative process. We have an initial state here labeled S0, and we can follow the edges in the picture from left to right until we reach a terminal state, which is marked with a square. We think of the terminal objects as representing terminal states as representing completed objects, like the molecules or smiley faces that we're trying to generate. And we learned in the last talk that when we assign a number to every edge, a flow, we can extract from this flow a policy, which is, just as in RL, a way of getting a distribution over subsequent states when we're sitting at a particular state. The way we turn a flow into a policy is by taking the flows to all of the children of the state we're at and dividing by the sum. In other words, normalizing to get a probability distribution. So for instance, we may be at S0, so we look at a flow to S1 and to S2, and our policy goes to S1 or to S2 in proportion, with probability proportional to the flow to S1 and to S2, and so on until reaching a terminal state. What we're trying to achieve through any GFlowNet training procedure is to make the marginal likelihood that the policy will terminate in a given completed object proportional to its reward. And the main result that Emmanuel covered in the last talk is that when we enforce a local condition that at every state the flow in equals the flow out, the policy that's obtained from this flow happens to sample proportionally to the reward. And this is the first main theorem of GFlowNets, that if flow matching is satisfied at every state inside the state space, then the corresponding policy samples in proportion to the reward. So nothing new so far. But there are some problems with this objective, which Emmanuel already alluded to. So let's go through those. The first one is that it's a local objective. That is, the objective at a particular state depends only on the flows into and out of that state, not other ones in other parts of the state space. Now, when we perform an update at one state, we still might affect the edge flows somewhere far away. And that's due to the neural net parameterization of flows. So the flow function is given to us by a neural network. And so we change the parameters when we update the edge flow in one part of the graph. So it might affect the edge flow in another part of the graph. This is important for generalization. On the other hand, this locality still has a limitation. And this limitation is something that happens in other reinforcement settings as well, and it's the problem of slow credit assignment. I can illustrate it with this figure. So imagine that, our graph is going top down here. So imagine that we sampled our policy and we saw a very high reward state, this X at the bottom. And the flows on the edges along this trajectory were very small. So what will happen? Which edge flows will get updated when I got this very high reward state? Well, the flow matching might be very close to satisfied at all of the states in the beginning of the trajectory where their flows are small. So the only place where there's a discrepancy would be at the very end, where the inflow is small, but we got a high reward. So I should increase the edge flow there. So the only update happens near the end. So now this edge there now gets a higher flow through a gradient update. So now what has to happen to propagate this information about a high reward state closer to the beginning of the graph? Well, we have to see this previous state. And so until I see that state again, I won't get any update. So imagine I saw this state again. Now the outflow is high now, but inflow is still small. So now that one has to be updated, and the signal is propagated one step closer to the initial state, and so on. And if trajectories are long, and the likelihood of reaching these states is small, it can take a very long time to get an update to flows or policies near the beginning of the trajectory when we have an interesting state at the end. This is the problem of slow credit assignment, and it's a major limitation of GFlowNets with local training objectives. Now, another problem with flow matching, which Emmanuel also mentioned, is the possibly high computation cost. We usually, when we train models with flow matching, we have a model which takes in a state and outputs simultaneously the edge flows to all of the subsequent, all of the children of that state with a single neural network. Usually, actually, the model is outputting the logs of those states, but that's not what's important here. So flow matching is trying to enforce that inflow equals outflow. And computing the outflow is easy in this green rectangle. We just have to evaluate our neural net and sum all of the edge flows that it outputs, the flows to all the children. But computing the inflow is not so easy, because we would have to evaluate our model at all the parents of the state of interest. So if there are n parents, then to compute the flow matching loss, we need n+1 neural net evaluations to compute the loss. And for problems with many parents for any given state, this can be prohibitive. So that's a problem. We want to avoid that. And this observation is what motivated the introduction of the first loss that's not flow matching, called detailed balance. So I will introduce this one next. So the idea of detailed balance is that instead of working with edge flows, we'll introduce a different parameterization. So we will directly learn the policy, the policy, which is a distribution over children of every state in the graph. It's just like in reinforcement learning, it's output by a model which takes a state as input and gives us the logits of all of the possible actions, all of the possible children. And in addition to the policy, we need some auxiliary objects. So I'll explain them in reverse order. So we need a special object called the backward policy. And I'll talk a little more about what it actually means in a while. But you should think of it as a policy which can start at a terminal state and sample backward until getting to an initial state. So it's a distribution, or a model that gives a distribution over the parents of any state in the graph. And this looks a little funny because why would we ever want to start at a terminal state and sample backwards and get a trajectory that leads there? But this can actually be useful, as I'll talk about near the end. And in addition to those, we learn a single estimator, a neural net that gives us one number, a scalar, for every state, called the state flow. And you should think of this as, so when flow matching is satisfied, then flow in equals flow out. And they're both equal to something called the state flow. It's the amount of water flowing through the state. Now, how is this parameterization related to the one used in flow matching? So if we look at the forward policy and how it's defined in terms of the flow, so this bottom left here, the likelihood of passing to a child V from a state S is proportional to the flow from S to V. So it's the flow on the edge S to V divided by the sum of all the flows coming out. And similarly, the backward policy can be defined in terms of a flow. So instead of normalizing over all of the children, we normalize over all the parents. So to decide which parent to transition to, the backward policy takes the flow to all the parents and normalizes to get a distribution summing to 1. So if we look at these two equations, we see that there are two different ways to express the state flow just via algebra. The state flow is, on the one hand, the outflow of the parent times the forward policy, the likelihood, so the outflow at S times the likelihood of transitioning from S to S prime. And on the other hand, it's the inflow at S prime times the backward likelihood. So the backward policy's probability of transitioning from S prime to S. So the key part here is the equality of these two ways of writing the edge flow. We can visualize it also on the picture on the right, where these two quantities, inflow at S prime times backward policy, or outflow at S times forward policy, are both supposed to be equal to the flow on the edge from S to S prime. So now some magic happens, and we turn this equality into a training objective. So remember that we're learning F and the backward policy PB and the forward policy PF. So we take this equality and make it a constraint that we try to enforce. So the detailed balance objective for an edge from S to S prime is trying to make these two quantities equal. So this is just like the flow matching constraint, inflow equals outflow, is turned into objective, log of inflow divided by outflow squared. We do the same thing here. And just like in flow matching, this we can stabilize this by adding small smoothing constants to numerator and denominator. And let's take a closer look at this last. So first of all, this is written as a log of some products and quotients, but because we're outputting flows in the log domain, and because we're outputting our policies through their logits, we can do some algebra and turn this into just a sum of logs squared. So it's just a quadratic loss in terms of the logits and the state flows. And let's also think about what happens at the terminal states. At the terminal states, we know that the inflow is supposed to equal the reward. And with the detailed balance loss, because the inflow and the outflow are the same thing as the state flow we're learning, we can just force that the state flow equals the reward at terminal states. So this is like a boundary condition that we enforce, in addition to this detailed balance objective, which has to be satisfied on every edge inside the graph. And from the algebra on the previous slide, we can see that if the detailed balance constraint holds on every edge, then the edge flow that we recover from it by writing the edge flow as state flow times policy satisfies flow matching. So by the first main theorem about GFlowNets, the policy is sampling proportionally to the reward. Now, this parameterization involves no edge flows. It involves two policies and a state flow. We can reduce the number of objects involved by fixing the backward policy to some simple distribution of our choice. I just want to note this here, and I'll come back to this a little later. Okay, so we have detailed balance, and it solves the problem of summing over a large number of parents because it depends only on a single edge. But it's still local, and so it still has the credit assignment problem that I discussed a few slides ago. So it would be nice if we instead had a trajectory level objective. That is one that sees a reward from a terminal state and immediately sends a gradient update to all of the edges seen along the trajectory. And we struggled with that for a long time to find such an objective. We first came up with it in the case of a tree-shaped graph where states only have one parent. And then eventually we had this realization that we can get a simple trajectory level objective, which I'll derive for you now. So now comes the mathiest slide of the presentation. So I promise it's only downhill from there, or uphill, depending on how you see it. So let's look at a trajectory. So it starts at the initial state as 0, and it takes n steps, ends at a state Sn, which I also call x. X is usually a terminal state. And let's write the detailed balance constraint on each edge. And I write it in this way, in the same form that it appears in the loss. So f times pf equals f times pb. So I write that the quotient equals 1 for all of those transitions. And Sn is a terminal state, so the flow at the terminal state equals the reward, R of x. So all of those equal 1. Now, let's take all of these constraints and let's multiply them together. So they're all equal to 1, so their product equals 1. So I've done nothing here, just multiplied all the equalities in the first line. Now, a lot of cancellation is going to happen because the flow in the denominator of one term cancels with the flow in the numerator of the next term. So all these flows cancel, except the very first f of s0 and the very last r of x, and we're left with this. So I've just done some rearrangement of terms. So let's look at this. So in the numerator, we have the flow at s0, and then the product of all of the policy's transition probabilities along the trajectory from s0 all the way to Sn. And in the denominator, we have the reward, and then the product of backward transition probabilities as we start from x, and then we go backward along this trajectory. And no other state flows survived. Now, that's pretty nice. So we have this so-called trajectory balance constraint, which says that this numerator and this denominator are equal. Now, I can also write it in this condensed form. So flow at s0 times a forward likelihood of that whole trajectory. Pf of tau just means the product of those transition probabilities in the numerator equals the reward times the product of all the backward transitions in the denominator. Now I write PB of tau given x because the backward probability of a trajectory only makes sense if I know where to start that backward trajectory at a given terminal state x. So when we have some constraint in GFlowNets, we want to turn it into a loss. Let's do that. For a trajectory, we just enforce with the same kind of squared log ratio trick. We enforce that these two quantities are equal. So the log of initial state flow times forward likelihood of the trajectory, divided by reward times backward likelihood of the trajectory squared. We're supposed to minimize that. So this objective is trajectory level. So it depends on all of the transitions and their forward and backward probabilities. So when we see a trajectory and we get a reward, we immediately get an update to all of the transitions that we had in the trajectory. So it's a global objective. Now, there's a theorem, and it's not exactly obvious that why it holds, that if we make this objective hold, so if we make f times pf equals r times pb for every trajectory, this is sufficient for the forward policy to sample proportionally to the reward. So the derivation I showed shows it's necessary because from detailed balance through this cancellation we get trajectory balance, but the other way requires doing some math. So practically, what do? We sample a trajectory from our policy or from some more exploratory version. You'll hear about that in the next talk. And we perform gradient updates on this TB objective. Let's take a closer look at what properties it has. Now, I've already said this is a global objective, so it leads to faster credit assignment due to yielding a gradient update to every state along a trajectory when a reward is received. In addition, it doesn't require learning the state flow for every state, for every state, only for the initial state, f of s0. Everything else canceled in our derivation. And just like Emmanuel mentioned before, the f of s0, which we do have to learn, at convergence ends up being equal to the total reward, so the sum of all rewards of terminal states. We use the letter z to denote that often. Now, here's a point which is very important in understanding GFlowNets as a variational inference algorithm. The TB loss is actually doing something with a deeper meaning. So it's equating or trying to make equal two distributions, not over states, but over trajectories. One of them is the distribution over trajectories that you sample by starting at the initial state and then sampling the forward policy. The other one is the one that you sample by taking a terminal state sampled from the true reward distribution. Now, we can't usually do that, as we want to learn. And then following the backward policy from that state back to the initial state as 0. The trajectory balance objective is trying to make those two distributions over trajectories equal by making the ratio of likelihoods equal to 1. So one consideration that falls out of that is that we can actually fix the backward policy. So given a terminal state, we can just decide once and for all from the beginning, without having it learned, what is the posterior distribution over trajectories that will get us to that state. We can, for example, make the backward policy uniform. So that's a common choice because it often simplifies, it reduces the number of models we have to learn. When I'm just starting to prototype a GFlowNet, I often just start with trajectory balance with the uniform backward policy because it's very simple. If we fix the backward policy at every state to be uniform over the parents, then the only things we have to learn are the initial state flow and the forward policy. Very simple, right? So it's just like in reinforcement learning, where we just learn a policy, or maybe sometimes a value function, except we just have to learn one extra thing, which is the initial state flow. And a practical consideration is that this initial state flow we often learn in the log domain, and it often helps to set a higher learning rate on that because it can be trained stably even with a high, even with large updates. So just some results. As we saw, trajectory balance allows you to find more modes and converge faster generally than other training objectives. On the bit sequence task, here's a molecule domain where we first implemented and tested trajectory balance. So we get more stable training, more modes discovered, and so higher diversity and higher reward of the typically generated objects. Now, I want to conclude with some practical considerations about how to choose an objective. So you want to train a GFlowNet for your problem. You decided what objects you want to generate. You designed the state and action space. So you decided the generative process that you're going to use. So what objective should you use? Well, so I think that trajectory balance is a good objective to try by default because it's fairly simple to implement and it yields fast credit assignment. On the other hand, it has some limitations, which are that it can have a high gradient variance and a high memory cost, especially if the trajectories are very long or there's a very high range of rewards that you encounter. So sometimes you might want to try something based on flow matching or detail balance instead. Now, in general, detail balance does not work as well in settings that we often encounter, unless some special constraints are satisfied. There's a trick called the forward-looking flow parameterization, in which if you can compute some kind of proxy reward at not complete states, at incomplete states, intermediate states, then you can parameterize the log flow function, not directly through a neural network, but as an additive correction to this proxy log reward. And if there's interest, I can give a few examples of that in the questions. There are similar tricks possible if from every state it's allowed to terminate, which is the case in some generative problems. There we can also learn the flow function as a correction to the reward of that object if we chose to terminate there. And there's another objective called subtrajectory balance, which I won't go into, but which is a kind of interpolation between detail balance and trajectory balance. So Trajectory balance learns from an entire trajectory by multiplying together the detailed balance constraints and then canceling all the state flows. Detailed balance learns from a single edge. So subtrajectory balance does this, but takes a partial trajectory, starting not necessarily at S0, ending not necessarily at a terminal state, and performs this cancellation so that only the state flow at the start of the subtrajectory and at the end are remaining. And combining the detailed balance, edge level, trajectory balance, full trajectory level, and subtrajectory balance for partial pieces in the appropriate way can give us the best of both worlds in terms of stable training with the low gradient variance coming from detailed balance and fast credit assignment that comes from trajectory level objectives. So I will finish with that, and here are the main references for the losses and ideas I've discussed. And you can check out any of those if you're interested. Thank you. We're a little behind schedule, but we have 5 minutes for questions.
Hi. Yeah, thank you for the nice presentation. I have a question about how to choose, how to get samples. So I remember that in the training process, MNL mentions that policy could be off policy, but in practice, which policy do we should choose?
That's a good question. So we know that for the forward policy to sample proportionally to the reward, trajectory balance or detail balance or flow matching has to be satisfied at every state or at every edge or at every trajectory. So we are actually free to choose any training policy we like as long as it has full support. Now, what we do in practice, this is the subject of the next presentation, but just to give you a preview, common techniques are some modification to the on-policy training, like introducing random actions or tempering, as well as using information about known terminal states, such as those obtained through a replay buffer. So if we have interesting terminal states, we can train on backward trajectories sampled from them. But you'll hear more in the next talk.
Thank you. Can I ask another question? How can we choose the length of sub-trajectory in practice as well?
For sub-trajectory balance?
Yeah.
Well, that's an interesting question. I don't know the best answer, but what we did in the paper on sub-trajectory balance is we took all of the sub-trajectories and we weighted them in proportion to some constant lambda to the power of the length, which is inspired by a technique called TD lambda in reinforcement learning.
Okay. Thank you.
Considering the trajectory balance objective, you said that sometimes common practice is to set the backwards policy to a uniform. I have a hard time understanding how this wouldn't just enforce the forward policy to also be uniform. How does this actually let us still sample proportional to the reward?
Well, first, the theoretical side of that answer is that for any backward policy you choose, there's a unique forward policy such that together they optimize the trajectory balance objective. Now, how do we understand that? So we think of TB as equating two distributions over trajectories. So let's start with this backward distribution. We can sample it by taking a terminal state from the reward distribution, which imagine Oracle can sample for you, and then sampling uniform backward policy. So that distribution over trajectories can also be sampled forward. And if those two distributions are equal, then their marginal distributions over the terminal state are also the same. And for the backward one, by construction, it's the reward distribution. So for the forward one, it has to be the same.
Oh, I see. Thank you.
And yeah, I suggest you can read the paper on GFlowNets and variational inference for a discussion of this.
Thanks for the talk. I guess my question is, what if you cannot enumerate the parents? If it's just too difficult? Because even for the backwards policy, I guess you have to know how many you have.
Yes. So the question, as I understand it, is even if you're fixing the backward policy to uniform, so 1 over number of parents, you still need to know how many parents there are. And no, if you have never gotten your hands dirty with GFlowNets, it might not make sense why that can even be a problem. But in fact, it can be. For example, in molecule generation, when there are many ways to remove a component from a molecule, you may get possible parents which are equal due to isomorphism. So there are different construction orders for the same molecule, and it's a difficult graph isomorphism check to determine if two ways of expressing the same molecule are actually the same. So, well, there's nothing you can do about that. You have to do an isomorphism check on the parents. I don't have a better answer. Okay, you can do faster isomorphism checks if you learn if you have a learned hash or embedding for the parents, which allows you to quickly determine if two molecules are isomorphic.
But yeah, that could arise in other settings where hatching a graph is not necessarily the answer. It could be also in domain uncertainty of. But anyway, so I guess the answer is you can't. You have to find a way to enumerate the parents.